Welcome to Maths with EJD. I've been taking series of videos on basic calculus and specifically integration in the last few videos. So in this video, I'm just going to show you some basic integration formulas, that will come in very handy. And of course, several practice questions for you to try your hands on. So first of all, look at the formulas right before you. You'll find them very useful. The list below shows some basic integration formulas. The first one, if you integrate a constant with respect to x, it just takes x on and you add the arbitrary constant, and that k is any number, right? Then if you have x raised power n dx, that's the polynomial integration I talked about. So you have x raised power n plus 1 over n plus 1 plus constant c, arbitrary. And of course, n has got to be not minus 1, because if it is minus 1, that will be, it will make the expression infinite, right? It will make it not defined. Therefore, 3, it's more like the case of 1 over x dx. So when you that's the derivative function ratio integral, which will just be ln of the denominator. Okay. And if you integrate e raised power x dx, any exponential function straight like this, you always get e raised power x back plus c. So if you integrate e raised power x 1 million times, just like if you differentiate it 1 million times, you keep getting e raised power x. I think I'm going to do a proof for that in one of my short videos, like that. Then of course, if you have integral of a raised power x dx, so you are going to get, so if you integrate, you're going to get a raised power x over ln a. In fact, I believe the approach you need to use here is that idea of integration by parts. I think that's what is going to work here. Then if you integrate sine x dx, you get minus cos x plus c. If you integrate cos x plus dx, you get sine x plus c. If you integrate sec squared x dx, you get tan x, because of course, if you differentiate tan x, you get sec squared x dx. If you integrate cos squared x dx, you get minus cot x plus c. If you integrate sec x tan x dx, you get sec x. Because if you actually differentiate sec x, you get sec x tan x. If you do that, that's what you get. Then if you integrate cosec x cot x dx, you get minus cosec x plus c. If you integrate tan x dx, you get ln sec x plus c. Then if you integrate cot x dx, you get ln sin x plus c. If you integrate sec x dx, you get ln sec x plus tan x plus c. I mean, you can try all of these things out for yourself to see them. Then the 15th one, if you integrate cosec x dx, you get minus ln cosec x plus cot x plus c. If you integrate sin x dx, that's hyperbolic sine, you get cos x dx. I mean, cos x plus c. So it's more like the whole idea of if you integrate sine, you get cos. Just like if you differentiate. But here, if you integrate sine, you get minus cos. So if you integrate sine here, you get minus cos. But if you integrate sine, so you have to pay attention to that. The sine thing doesn't come in. So if you integrate sine, you get cos. But if you integrate sine, you get minus cos. When you integrate sine, you get cos, like that. So if you integrate cos, you get sine. So the sine thing doesn't affect the hyperbolic functions as far as sine and cos are concerned. Then if you integrate dx, which is square root of a squared minus x squared, you get arc sine of x over a. And of course, that is going to take the approach of trigonometric substitution. Same for number 19. If you have dx over a squared plus x squared, you have 1 over a arc tan x over a. Then if you have number 20, you have dx over x into x squared minus a squared. Still the integral trigonometric substitution thing. Then same here again, you have sine coming up here, and then lastly, if you have this, you have that cos inverse integral of dx all over x squared minus a squared. You have cos inverse x over a. So those are some general formulas that you find very useful as you deal with integration. So that takes us to some exercise. I have several of them under integration for you to try your hands on. So let's talk about some exercise like that. So first of all, you look at this, you want to evaluate the following: 6x raised power 5 plus 5x, all the 1 to 3. So you see all of those, you can simply, for the first one, you can integrate directly, that's polynomial. For the second one, you can divide through by x squared and you integrate. Then for the third one, well, you may be tempted to think of using integration by parts, but that'll be too much stress. You can just easily expand these things and you get your results. or better still, 6x. Oh, okay. Well, I mean, it's better to just expand and get your results. Then for for the next one, right? It looks like if you differentiate the denominators, you get the numerators or something close to them. So you can use that idea. So differentiate denominator, you get numerator. Then you are going to, so you may need to do some maneuvering to end up getting lean of some seven, whatever is at the bottom, with maybe sometimes some number in front to balance things up. I've taken such examples in the past. So here you want to evaluate cot WDW sec x dx. These are integral of trigonometric functions, right? Sec x dx cos squared x dx cosec y dy cos 5y sin 3y dy cos 7z sin 4z dz. So if you check the formulas I showed you, if your answer is correct, you will know because I've put some of those there. I mean, this particular one is like what we did when we're integrating sine squared x. You know, you need to use some trig thing. So also this one requires some trig maneuvering. So like that. So you can try them out. If you have problems with them, you can let me know in the comment section. So I may have to do some fast math solution sections, for this if you have issues with them. Okay, and here you definitely need, I think here you need substitution, probably algebraic, most likely algebraic substitution all the way. Yeah, for all this, you need algebraic substitution to be able to handle them. Then you also have this. Absolutely, here you're going to need polynomial. What is that thing called? Trigonometric substitution. So you need trigonometric substitution to solve all these ones. And then okay, I think we have a few more slides to go. Okay, so here, what do you need here? Evaluate the following. Yeah, this looks like integration by parts. Yes, integration by parts. That's what you need for this integration by parts. Then here you need what would you need here? I guess here you need integration of compound fractions. So you have to resolve the bulk of this into partial fractions, and then you integrate. Yeah, that's what you need here. Integration of mostly here you have compound fractions that you need to integrate. I think this is an oversight. This should be the theta. So we're integrating with theta here. I think every other thing is fine. You have dt, you have dp du, dx, dy, dz, dt, ds, dx, dy, dz. Okay, so d theta for this. Then, so that's all about that. And if you need some material that can help you, please check this out. Engineering Maths first aid kit and all that. You can use this. So look at the questions again and try your hands on them. They are very useful for you. So see you in the next video. In the next set of videos, I'll be talking about applications of integration. We've talked about integration all the way. So I'll be talking about applications of integration. So if you have not subscribed, make sure you do that so you can get and press the notification bell, right? So you can get alerted anytime I release a new video. Thank you so much for listening. See you in the next one.